Hello and welcome to CO 738 Probabilistic Methods. Today we'll be proving Pippenger-Spencer. So what is Pippenger-Spencer? So to remind you, the theorem we'll be proving today says that for every r at least 2, k at least 1, a greater than 0, there exists a gamma and a d naught greater than 0, such that for every n and capital D bigger than d0, the following holds. If H is an R-uniform hypergraph on n vertices with minimum degree at least 1, and we know that every vertex has degree roughly d, and every vertex has degree at most kd, so again the first condition only, but at most gamma n of them, so you're allowed some to not be quite d, but the second condition says the maximum degree is bounded, and we know that the co-degrees are sufficiently small, then H has a cover of at most 1 plus a n over r edges. So we used this last lecture to prove Rodl's theorem, proving the Erdos-Shanaani conjecture by reducing that problem to this problem about covering hypergraphs. So again, a cover, if you recall, is a set of edges where every vertex appears in at least one edge. And what I just said in more layman's terms is that small covers do exist, so n over r would be optimal if an R-uniform hypergraph is roughly regular of degree d, where d is sufficiently large, the max degree is linear in d, and the co-degrees are sufficiently small. So this was our Pippenger-Spencer theorem. Now technically Pippenger and Spencer actually proved a harder theorem showing that you can actually, quote, color the edges. So you can partition them into not covers, but what are called packings or matchings of roughly this size. So you can actually get all the edges in this way. But we won't be doing that proof. Again, we'll just be doing this one. The other proof, the harder one, is similar, where you're going to be somehow constructing many matchings simultaneously. But so we're going to do it from the covering perspective, and again, we're just finding one. And what was the proof idea was to use Nibble. So we let P be epsilon over D, and we chose each edge independently with probability P. And we let E prime be the set of selected edges, and we are going to show with high probability that E prime is roughly PEH, which is approximately an epsilon fraction of the edges, n over r there. So that's one thing we're going to show. That'll be number 4. 5, that the number of vertices covered more than once is roughly epsilon squared n, so hence E covers at least epsilon n minus on the order of epsilon squared n. So basically there's almost no overlap. So this is actually quite good. We're only, again, nibbling. We're only doing a little bit of this cover at a time, but we're going to do a step where it covers a small fraction, but without too much overlap. And then we'll show that the remaining induced hypergraph on uncovered vertices satisfies the conditions from before for new parameters, though. And then we're going to proceed to iterate this procedure until only about epsilon n vertices remain, at which point we can finish by just taking one edge for each remaining vertex. So again, this is how Nibble generally works. We do a little bit at a time. We iterate, making sure certain properties are preserved, and then we do some sort of finish to get the desired object. So that was our outline from last time at a high level. The purpose of today's talk is to formalize this, to give an actual proof, to go through the, quote, gory details. So we're going to be using the second moment method, which we learned last week, to go ahead and prove that with high probability these things really do happen. So let's formalize that iterative step into one iterative lemma. It goes like the following. So again, we'll have R, the uniformity, we'll have this K coming from the max degree, and then now we're going to introduce two new parameters. So instead of an A, which is somehow the error in the cover, we're going to talk about epsilon, which will be that small proportion we're nibbling, and a, quote, gamma prime, that's going to be greater than 0. And you'll see what the purpose of that is second, and then we'll get the outcome, that there's a gamma and a d naught, and for every n d, at least d0, the following holds. If H is an R-uniform hypergraph on n vertices with minimum degree at least 1, and you need the minimum degree at least 1 because you need every vertex to be in an edge to try to get it covered, and satisfying that 1 to 3 of those conditions of Pippenger-Spencer hold, then there exists an E prime, subset of the edges, so this will be our selected set, which satisfy these properties. So let's formalize that. So condition 4 will be that E prime is epsilon n over r times 1 plus or minus gamma prime. So it'll be a little off from what we are somehow expecting. And then the set V prime, we're going to call it, which will be V minus the edges in E prime. So that's the uncovered vertices of V. So V prime, the uncovered vertices will be of cardinality, V prime being n e to the minus epsilon 1 plus or minus gamma prime. So we'll still be quite a large proportion of the vertices. And there'll be, again, some tolerance there with this gamma prime. So that formalizes part 5. So we've gone ahead and done that. And then part 6, we have to somehow show we can iterate. So that's going to be condition 6 here. The outcome 6 will be that for every vertex in V prime, so every uncovered vertex, but at most gamma prime V prime of them, that the new degree on H of V prime of X will be D times e to the minus epsilon of R minus 1, 1 plus or minus gamma prime. So just off by a little bit. So we're going to have somehow a new degree. So the degree has clearly gone down from roughly D to this somehow this e to the minus epsilon R minus 1 factor. So it's gone down by a little factor. But again, we're roughly regular. So we're going to talk at the end, what about the other conditions? So that says we satisfy somehow that first condition of Pippenger-Spencer, that we're roughly regular. How do we know we have still acceptable max degree and acceptable co-degrees? The solution is, well, before the max degree was not too large and before the co-degrees were quite small. And so we'll just retain those naturally, that those won't go up by deleting vertices and edges. All right, so that's the main thing to show. We've now formalized, so we're going to show this iterative lemma, and then at the end of the lecture, we're going to iterate the lemma to prove Pippenger-Spencer. So the iterative lemma is the hard part. It's the main thrust, and this is quite typical of the Rodl Nibble, that you have this iterative lemma or iterative procedure, and you need to show that it holds until you then finish, put all the things together by iterating it. All right, so that's our plan. Let's talk about the proof setup. So throughout the proof of our iterative lemma, we will assume that D and N are large enough when required, which of course we're allowed to do. And we will let gamma 1, gamma 2, etc. denote constants, where for every I, gamma I will go to 0 when gamma goes to 0 and D goes to infinity. So what was happening here, again, the point is we want an outcome. There will be this gamma, so gamma prime, if you remember, we're given it's a knob, right? So the idea is that, you know, we have, we're going to have the knob, gamma prime is what amount of somehow error or irregularity we're allowed coming out of the theorem. And we need to say then there is some gamma, which when you put it in, when you start with that amount of regularity, you get this much out. And we need those to go in tandem, right? And that's what the purpose of these gamma I will do, because by choosing the gammas small enough, by choosing gamma small enough and D0 large enough, which also lower bounds the degree, we'll get for free that the gamma i's will be smaller than gamma prime, right? There would be some choice of gamma, which makes all of the irregularities that we'll be tracking smaller than the gamma prime, the one we're allowed to tolerate. So that's the idea. So it's just a kind of a notation to say that these indeed are such functions. I'll try where we can to talk about what specifically they are. They're just somehow functions of gamma. They might be 2 gamma, 3 gamma, such things. But we'll go through that and point them out when we can, but there'll be a lot of them. So otherwise, we could have used little o notation. So basically, we're saying if you think of gamma as, little o of 1, then these gamma i's are also little o of 1 and such. But here we're doing it a bit more formally, following along with Spencer. All right, so now what's the main plan? Again, is we're going to let E prime a subset of the edges of H, where each edge E is in E prime independently with probability P. P will define to be epsilon over D, as promised from before. So that's our probability space. That's our probabilistic setup. And then we have to show that with positive probability, all of 4, 5, and 6 hold for E prime. And we do this by showing that each of 4 to 6 holds with probability at least, say, 0.99. So then they will indeed all hold, with probability 0.97 by union bounding. So that's our plan. So we'll show that each of them holds with high probability. All right, so let's go through the details. So we're going to do 4, we're going to do 5, we're going to do 6. So we take each one at a time. We will somehow calculate the expectation. We'll look to the second moment method to do variance, to use Chebyshev's inequality to go ahead and show that these indeed do hold with high probability. So that's our plan for the iterative lemma. On to the proofs. So the proof of 4, which again is about E prime, let's start with the expectation. To do that, we'll upper and lower bound the number of edges of H. Since H has at least 1 minus gamma n vertices of degree 1 plus or minus gamma d, we know the number of edges of H is at least 1 minus gamma n times that lower value, 1 minus gamma d, all divided by r, since we sum up the degrees, and then it's r uniform. So each edge will have r vertices. So that'll be at least 1 minus 2 gamma n d over r, as you get 1 minus gamma squared. You can lower bound that with 1 minus 2 gamma. And we get 1 minus 2 gamma n d over r. The upper bound, if we use the fact from above and that the max degree of the remaining vertices is at most kd, we get that the number of edges of H is at most 1 minus gamma n times 1 plus gamma d, plus for the remaining gamma n kd, and again divide all by r, and we get 1 plus k plus 1 gamma n d over r. So we know that it's roughly nd over r with some factors of gamma. So if we set gamma 1 to be the maximum of 2 in k plus 1 times by gamma, then E of H is 1 plus or minus gamma 1 dn over r. And then by linearity of expectation, we know the expectation of E prime is p times E of H, which is then, since p is epsilon over d, the big d's will cancel, and we'll get 1 plus or minus gamma 1 epsilon n over r. So that's the calculation for the expectation of E. Now we turn to the variance and Chebyshev's inequality to show that actually it's with high probability close to that. So what about the variance of E prime? Since the edges are chosen independently, the variance of E prime is the sum of the variances, which will be E of H times P1 minus P, which is of course the most PH, which is at most 1 plus gamma 1 epsilon n over r from previous calculations. And then by Chebyshev's inequality, what's the probability that E prime is far from its expectation? So let's say at least gamma 1 of the expectation away. So an additional factor of gamma 1 away, it'll be the variance of E prime over gamma 1 squared expectation squared, which if you work out, it's this somewhat weird number. You get like 1 plus gamma 1 up top, and you get gamma 1 squared, 1 minus gamma 1 squared, epsilon n over r. And then where do we go from there? Well, since n is large enough, we'll know that this is actually quite small. Then it will be at most 0.01 if n is large enough as factors of gamma 1s and epsilons and r's. All right, so then that has saved us. And now if we set, say, gamma 2 to be 2 gamma 1, and then the probability that E prime is 1 plus or minus gamma 2 epsilon n over r is at least 0.99. And this, therefore, proves 4. So if we kind of say an additional factor of gamma 1 away, so the expectation we couldn't exactly nail down, but if we then allow a little bit more irregularity, we can indeed get that with high probability using Chebyshev's. So that was the proof of 4. On to the proof of 5. So here we're going to be studying V prime, the uncovered vertices. So for every x in V of H, let Ix be the indicator random variable where Ix is 1 if x is uncovered, so if x is not any of the edges of E prime. And then we note that V prime is indeed the sum of these indicator random variables. And now we try to calculate the expectation then. So what's the expectation? Well, it depends what kind of vertex it is. If the degree of x is 1 plus or minus gamma times d, then the expectation of Ix would be 1 minus p to the d of x. So again, why is that? We need to be uncovered. We need that every edge around, and there are d of x edges, to not be chosen. So 1 minus p, and those are all independent, of course. Now that's equal to 1 minus epsilon over d, because that's what p is. And again, the degree is 1 plus or minus gamma d. And you can work out that that is indeed e to the minus epsilon with a little bit of error that depends on gamma, which we'll call gamma 3. But again, it's a going to 0 type function as gamma goes to 0 and d goes to infinity. So again, you can see that because 1 minus epsilon over d to the d is roughly e to the minus epsilon with some error that depends on d. And then we have some additional error with the exponent, but we can sweep that all into this gamma 3. So I won't state it specifically. So that's if the degree is roughly regular. We know what the expectation is. What about the other ones? Well, for the most gamma n other vertices, we'll just use a very simple bound. The expectation of the indicator variable is somewhere between 0 and 1. I mean, it's either in or out. So that's not saying a lot. That's not a very good bound at all, but there's so few of them it won't matter. So when we do the linearity of expectation, we'll have gamma n of these vertices, so that there'll be some error there since we can't really control the other ones. But on the other hand, the majority we could control with this plus or minus gamma 3. And so somehow if we then let gamma 4 be gamma 3 plus gamma, then we'll indeed find the expectation of V prime is n e to the minus epsilon 1 plus or minus gamma 4. All right, so we know what the expectation is, and it's close to what we want with some extra factor here with this gamma 4, but now we need to show with high probability it's actually somewhat close to that, maybe some additional factors of gamma. So we again turn to the variance, as we did previously for proving 4. Since V prime is a sum of indicator random variables, we know that the variance of V prime is at most the expectation of V prime plus the sum of the covariances of these Ix, Iy for x not equal to y and V of h. So here we're no longer maybe the sum of independent variables, but we have some covariances, so we have to work with those. What is the covariance? Well, it's the expectation of Ix, Iy minus the product of the expectations, which is then, what is that? The product of the expectations is they're 1 minus p to the dx and 1 minus p to the dy, so you get 1 minus p to the dx plus dy. That's the second term there. The first term, I claim, is 1 minus p dx plus dy minus dxy. So y, well, for each edge that either one of them is. How many edges are either one of them in? It's the sum of the degrees minus their co-degree. So that's what that exponent is. It's the number of edges with either x or y, and we need each of those to not be covered, to not be selected. So what good is that? Well, you could note that we could just factor out a term of 1 minus p to the dx plus dy, which of course is at most 1. So we can just upper bound this by 1 minus p to the negative co-degree minus 1. And then if you plug in that p is epsilon over d, and here we're using that the co-degrees are small. So then the co-degree is quite small. It's at most gamma d. Then this covariance will indeed be small. So it'll be at most some gamma 5. So again, it's going to be up to the d, 1 minus epsilon over d to the d is like e to the, minus epsilon there and such. Then we get plus epsilon once you put the negative sign in, but there'll be a factor of gamma there. So, that number is somehow close, to 1, and then when you're going to subtract off 1, there's this little bit, but it's going to be dependent on gamma. So we're indeed able to upper bound that by some function, say, called gamma 5. And so this is kind of one of the hearts of the proof. So for 4, it was a straightforward expectation calculation. Everything was kind of independent, so it worked. Here, when we're looking at the uncovered vertices, they're not independent, but the covariance is quite small, the covariances. And that's precisely because of the co-degrees. Since the co-degrees are small, the chance that they're, both uncovered is quite close to the product of those probabilities. All right, so now that we've done that, we can conclude that the variance from just plugging into above is at most the expectation of V prime plus gamma 5 of n squared. So each of those is some small number gamma 5. There's n squared pairs, I'd say at most. And that's, of course, at most some gamma 6 of the expectation squared. Since we knew the expectation was some legitimate number that's linear in n, then this just adds a little bit more error. So we can indeed say that the e of v prime is just linear in n, so that doesn't really matter. We can just sweep that in, since n is large enough, that into the gamma 6. So we get gamma 6 of the expectation squared. And then by Chebyshev's inequality, if we continue the finish, we say that the probability that v prime is far from e of v prime, what should far be here? If I use something like 10 the square root of gamma 6 e of v prime, then Chebyshev's tells you it's the variance over that number squared, which gets you 100 gamma 6 e of v prime squared. And remember, the variance is at most gamma 6 e squared, so then those cancel, and you're left with 100th, which is 0.01. And then, of course, this is a magic number because we're trying to show 0.99. So if we set gamma 7 to be 10 square root gamma 6, we know that the probability that V prime is within plus or minus gamma 7 of the expectation is at least 0.99. So 99% of the time, we're going to be within some gamma function of this expectation. And so then if we knew the expectation was, within some factor of gamma 4, so if you set gamma 8 to be gamma 7 plus gamma 4, then we'll be within a gamma 8 factor of this expectation thing, this n to the e minus epsilon that we were going after, with probability at least 0.99. And thus, this proves 5. That's what we wanted to do to show that V prime has high probability to be close to this n e to the minus epsilon, with some factors depending on the gamma there that, again, going to 0 as gamma goes to 0 and d goes to infinity. So we're going to move on with the proof of 6 now. So how do we prove 6? Well, this is a bit harder, right? We're trying to show that the new subgraph is roughly regular. So let me go through that. How does this work? Well, we know that all but at most gamma 9 n vertices V are in at most gamma 10 times d, what we'll call bad edges, those ones that contain a vertex of degree not in 1 plus or minus gamma d. So we have these irregular vertices. We'll call an edge bad if it contains an irregular vertex. And you can realize that only a small vanishing proportion of the vertices will be in too many of these bad edges. Why is that? Just there aren't many irregular vertices, and they have upper bound in the degree, so they really can't pollute too many edges. So I won't tell you exactly what gamma 9 and gamma 10 are, but indeed, somehow we can assume that most vertices are mostly, in quote, good edges. And for each good edge, that's the ones not containing an irregular vertex, we can actually figure out, well, the probability that that edge ends up in the uncovered subgraph. Because why is that? We would need that probability, we would have to have that all of the vertices are uncovered. And what is that? It's going to be all the edges that they're all in are uncovered. That's going to be 1 minus p, the chance they're not selected, but somehow the sum of all the possible edges. And you can realize that the sum of the edges is somehow the sum of the degrees of the vertices in this edge, except, we might have these co-degrees. So maybe plus or minus the sum of all their co-degrees, their overlaps. And the point is that the sum of the degrees, since they are again, not irregular vertices, are roughly on the order of d. So they're 1 plus or minus gamma times d. So we're going to indeed find that we're going to get an RD up there. Why is it R minus 1? So we're going to do this conditioned on an actual vertex being chosen. And then so we get that, and the codegrees are very small, so where we use the small codegree condition, it'll basically that'll just all get wrapped up into something we'll call gamma 11. And then, so for vertices, we can now actually say that the expected degree of a vertex, assuming itself was not covered, is going to be on this order of, you're going to get this 1 minus p to the r minus 1d factor. So again, you get that r minus 1d conditioning on one of the vertices, this v being not covered. So we get that factor for somehow each edge. It was in roughly 1 plus or minus gamma. If it's a regular vertex, 1 plus or minus gamma d edges. Except we have to somehow, couldn't control the ones that were bad. There were gamma 10d of those. So altogether we get e to the minus epsilon of r minus 1 times d with these irregularity factors. So you get some out front from, again, the degree we couldn't control, the bad edges we couldn't control, and then raising to this gamma 11, the problems with the codegree stuff. But again, that all gets swept into a 1 plus or minus gamma 12. Then we continue the proof. So now that we've kind of seen the probability, we can let IE be an indicator of a variable that the edge E is actually in H of V prime. And then we can conclude that the variance of the degree is both the expectations of the degrees, plus, and sorry for the typos, there's some brackets missing, plus the covariances, right? So we know what the expected degree is. We want to now look to the variance of the degree. And since it's an indicator of random variables, it's going to be upper bounded again, this formula of expectation plus covariances. And what are the covariances? Well, here it kind of depends on the edges. So there could be some bad edges. So let's ignore their covariance. So that's the second term there. We can upper bound that by plus 2 gamma 10 d squared, 1 plus or minus gamma. Since there's gamma 10 d bad edges, and if you're a regular vertex, you have 1 plus or minus gamma d. And might count it twice because, again, they're ordered pairs. So that's actually quite small. Again, that's only like gamma d squared, so gamma 10 d squared. So we can somewhat ignore that and focus in on the covariances of good pairs, where both edges are good. And we can do this by looking at the sum, this double sum for just one e, so we'll fix e. And we can note that there exist at most r minus 1 gamma d edges f, such that e intersect f is greater than 1. So somehow if you fix an e, again, there's just not too many edges with overlap there, right? There's just, because of the co-degrees, that just there can't be too much co-degree happening among the vertices that are in E. And then for all f with E intersect f being 1, we can also note that they just don't have many edges that go to both of them. So let's call that dE of f. So I'll think of degrees of edges as the number of edges they're in, and this is somehow the co-degree of the edges, and that's at most r minus 1 squared gamma d. They just can't have too many edges that intersect both E and F. So they also have somehow small co-degree, and that actually, in the same way as we did the covariances for the degrees of vertices, we can somehow do the covariance for these edges also ending up in the uncovered subgraph. Why? Because now for an edge to be uncovered, we need 1 minus p to the number of edges it's in, so it's kind of this degree of E, and the same for f, so you get d of E plus d of f in the second term. And similarly for the first part, where we're taking the expectation of them together, we need all of their common edges, the edges that are next to either E or F, to not be selected, which would be d of E plus d of F minus their quote co-degree. And in the same way as we did for 5, we can upper bound this by throwing out a factor of 1 minus p dE plus dF, because that's just at most 1, getting 1 minus p to the negative co-degree there, the dEF, minus 1. And again, the co-degree is quite small, and p is, again, epsilon over d. The co-degree is roughly, some factor, well, r minus 1 squared of gamma times d. So again, we'll get this to be roughly e to the epsilon gamma, but minus 1, so that's some function again of gamma, which we'll call gamma 13. So this is very similar to what we did with 5. We just had to be a bit careful, kind of throwing out bad edges that we couldn't control, the ones that have irregular vertices. We also had to throw out the bad vertices, the ones who were irregular to start with, and the ones who were also in too many of these bad edges. We threw those out, but we take it all together, and we can now do the finish, where the sum of the covariances will have r minus 1 gamma d for those edges. For a fixed, again, we're fixing E here. We'll have the edges which overlap F too much. There's not too many of those. And then for all the rest, we actually have quite small, we have like something gamma 13 covariance, and there's at most d1 plus gamma, edges to look at. So then we'll be done. We'll be quite small in something like gamma 14 times d. And as there are most d of 1 plus gamma edges E in this double sum, then what do we end up with? Because again, V is regular, so it doesn't have too many edges E or too many edges F. We've used that above. We get that the variance is at most the expectation plus this something like a gamma 15 d squared. So that's at most then, because we have this gamma 14d from the good edge pairs, we also had a little bit from the bad edge pairs, if you remember. So we get this little extra, little o of d squared there. And in total then we know that actually will be gamma 16, so it will be little o of the expectation squared. So it's again the expected degree, is on the order of d, and we have this little o of d squared, so that'll be altogether little o of d squared. The expectation again is some actual, some factor times d. So by Chebyshev's inequality with so if we want to shoot for some probability at least 1 minus gamma 17, we can determine that the degree, so here I'm using d prime to represent that awful dh of v prime above, then the new degree will be roughly 1 plus or minus gamma 18 of what we expected it to be, this d e to the minus epsilon r minus 1. So what is that saying? Somehow, yes, with high probability, each individual vertex should be within some gamma factors of this expectation, but we're not quite done yet, because we wanted, we now have to say, well, how do we actually do this, right? Do we union bound? What do we know with high probability each one is, but some might fall outside. But here's where we can use Markov. So we can apply Markov to get that with probability 0.99, all but at most gamma 19 n of the vertices satisfy the above. So there just can't be, too many violating this condition. So it's kind of unlikely. So with that, indeed, we have too many vertices that will fall outside. And so then we'll be done. So we somehow lose some of the irregularities. So we do this, we expect most vertices who are regular, who weren't in too many of these bad edges, to stay regular, again with some new degree, but we can't even control that exactly. We need to say, oh, okay, but, maybe some of them don't end up, well, we'll throw those as well into the trash, into the irregularity. So this proves 6 and completes the proof of the iterative lemma. Now we just have to iterate the iterative lemma to prove Pippenger-Spencer. So I won't go through all the details here, but you'd fix epsilon and gamma small enough. So according to some equations, you'll see. And we'll choose how many times we're going to run it. So that'll be time steps t. And importantly, we'll pick that e minus epsilon t is at most epsilon. So we want, when we're done, that there's at most somehow an epsilon fraction of the vertices uncovered. And then we'll apply the lemma t times. Each time the new hypergraph h of vi of uncovered vertices satisfies the following. It satisfies the conditions of our iterative lemma because it satisfies condition 1, but the degree is changed. It's gone down by this e to the minus epsilon r minus 1 factor. So di will be di minus 1 times e to the minus epsilon r minus 1, which will be, if you do it repeatedly, we started with d, it'll be d times e to the minus epsilon I of r minus 1, and that's because of outcome 6 of our iterative lemma. So we know that again, condition was that you're roughly regular. That was an outcome that we just proved, this number 6. What about the other two? I didn't really get into that, but as I mentioned long ago, yes, we still have condition 2, which is bounded max degree. It's just we changed, right? So before we knew everybody had degree kd, so now everybody will have degree ki di if you set ki to be kd over di. So there'll be more of a range for the max degree, but that'll be fine. And similarly, we'll have small codegrees where we just have to change what that means. We'll set gamma I to be gamma d over di. So then the codegrees will have the same bound. We're just changing what the acceptable parameters are there. So then we do that. Now to wrap up, you'll choose by reverse induction the various things. So we need to get to some gamma. We'll choose gamma t all the way down to gamma 0, so that gamma I prime will be gamma I plus 1, and so that the products of all of these irregularities, so these 1 plus gamma I terms, will be small, say at most 1 plus 2 gamma. Then we get that the VIs, what are they? They're VI minus 1 times e to the minus epsilon, except with these 1 plus or minus gamma I terms. But if we product all of those irregularities together from the above equation, we'd have a 1 plus 2 gamma error. So we'd have upper bounded, or really 1 plus minus if you want to do that. But v of h, and we get each time we get a factor of e to the minus epsilon, so we get e to the minus epsilon I. All right, so that's, you can figure out exactly how many vertices are left roughly at each stage. What about the number of edges? It's roughly epsilon times the number of vertices in I minus 1 divided by r, again with some error, this 1 plus or minus gamma I. And that you can upper bound by 1 plus 4 gamma epsilon n over r of e to the minus I minus 1 epsilon if you just use the equation above and the fact that 1 plus or minus gamma I is at most 1 plus 2 gamma from the equation. So you can do all that. You can say, oh, the number of vertices is this. The number of edges, so it's decreasing each time. The number of edges, we get an epsilon proportion, but again, also decreasing. But now you just can see that the final cover size has what? At most, you sum up the EIs over all the stages. That's the number of edges you get at each stage. And then we have to do that finish, if you remember. We have to pick an edge for each vertex left at the end. So we pick it for VT, and T should be lowercase t there, sorry for the typo. And that's at most 1 plus 4 gamma times epsilon n over r, the sum of these e to the minus I epsilons, and the Vt you can upper bound with 1 plus 2 gamma n e to the minus epsilon t. And what does that get you? Well, if you look at that first term, it's a geometric series, so we can upper bound it with epsilon over 1 minus e to the minus epsilon, and where we brought the epsilon in. For the right-hand term, we can indeed write this in terms of, since we're going to divide by r, and the second term doesn't have an r, we multiply by r, and we use the fact that e to the minus epsilon t is at most epsilon. But it's how we chose the t, so there's only a small proportion left. And then if you stare at that number, you'll realize that that's somehow at most n over r times 1 plus 4 gamma, something like 1 plus r plus 2 epsilon. So that number in the parentheses, the epsilon over 1 minus e to the minus epsilon, that denominator is roughly epsilon plus epsilon squared over 2, which will end up just adding some extra. So it gets you a 1 plus some extra factors of epsilon. And again, we get to choose now the, gamma and epsilon to get the A, and so indeed we can fold those in. So if you product it, it'll be a little bit of error. Some from the gamma, some from those factors of epsilon. This will be at most 1 plus A n over r, right? So as gamma and epsilon go to 0, that extra terms, the extra factor will also be going toward 1 there. So that will give us the cover as desired. So that was what we did today. We went through the proof of Pippenger-Spencer. That concludes the proof. We had a nice iterative lemma where we had to prove that E prime and V prime and the degrees, the roughly regularity, all held, that the various properties held. So now we could finish with this iterative application, iterating this iterative lemma to get to our final calculation. So that's the gory details of the Pippenger-Spencer proof. We use the second moment method, Chebyshev's inequality, to show that what we expected from those various variables in the random process were actually highly concentrated around them. So until next time, see you then!